In today's lesson, we're going to develop the terminology and the notation necessary to attack one of the more important problems of linear algebra, that of least squares analysis. As we go through the notational systems, make sure that you understand what the notation means and what it's telling you to do. The subspaces S1 and S2 of n space are orthogonal if V1 dot V2 is equal to 0 for all vectors in S1 and vectors V2 in S2. Now this is defining what we mean by orthogonal subspaces. So we have two subspaces, S1 and S2. They're both subspaces of Rn. These two subspaces are orthogonal if and only if I pick V1 from S1 and I pick V2 from S2. And no matter what V1 I pick, no matter what V2 I pick, V1 dot V2 is 0. Determine whether S1, defined to be the span of the vector -3, 0, 1, and S2, defined to be the span of the vectors 2, 1, 6, 0, 1, 1, are orthogonal. Let's let U be an element from S1. Then that means U is going to be C1 times a -3, 0, 1, which is going to be a -3 C1 0 C1. Let's let V be an element of S2. That means V, if V's in the span of S2, V is going to be C2 times 2, 1, 6 plus C3 times 0, 1, 0. Which would equal to, this is going to be 2C2 plus 0, so it would just be 2C2, be C2 plus C3, C2 times 1 plus C3 times 1, then it would be 6C2 plus 0. So this would be the form of V. Now if we do U dot V, to do the dot product, I multiply corresponding components and add them. A -3C1 times 2C2 is going to be a -6C1 C2. 0 times C2 plus C3 is 0. C1 times 6C2 will be 6C1 C2. And of course, a -6 plus 6 is 0, so we get 0. So therefore, S1 and S2 are orthogonal. So another definition, if S is a subspace of n space, then the orthogonal complement of S is the set S Now here's the notation for orthogonal complement, and it comes in using the orthogonal part with the perpendicular lines here. So this would be S complement is equal to the set of all vectors in Rn such that V dot U is equal to 0, where V is an element of S. So U is any vector in Rn, V is a vector in S. So the set of all vectors from n space such that the vectors times vectors from S dot with the vector from n space equals 0 would form the orthogonal complement of S. Well, let's do an example there. S is going to be the span of 0, 1, negative 1, 1. Find the orthogonal complement of S. Well, now we want V to be from S. So V, if I let V be any vector, is going to be of the form C1 times the 0, 1, negative 1, 1 vector, which is going to be 0, C1, a negative C1, C1. And we'll let U be from Rn. Now since we have 4 space here, n is going to have to be 4. So U would be a vector from 4 space. I can write it as a column vector. I can do either way, but I'll write it as U1, U2, U3, U4. So U is the vector, and I'm writing it as a column vector. I could also write it ordered pair notation, or ordered fourth notation, U1, U2, U3, U4. Now we want to find the set of all values for U1, U2, U3, U4 so that V dot U is equal to 0. Well, if we do V dot U, we're going to have 0 U1 plus C1 U2 U3 plus C1 U4 is equal to 0. That's when I do the dot product. I can factor out, now 0 U1 is 0, I can factor out the C1, and I'm left with U2 minus U3 plus U4 is equal to 0. Now we're going to look at the basis of a system that would make this true. In other words, we're going to think about solving the system. Now we could have the vector solution being, okay, since there's no U1 involved, U1 can be anything. So I'll let U be 1, 0, 0, 0. And we can see this would make it true because 0 times 1 is 0 plus all the rest of them are 0. So this is one solution to this equation. Now other solutions, we can look here and see that U2 is U3 minus U4. So if I say let U2 be 1 and U3 be 1, then U4 has to be 0. And since U1 could be anything, I'll let it be 0 this time, so I get another solution, which would be 0, and U2 is 1, U3 is 1, and U4 would be 0, and this makes it true. 1 minus 1 plus 0 is 0. Now if we let U2 be 1 and U3 be 0, then we get another vector, 0, 1, 0, negative 1. Because if U2 is 1 and U3 is 0, then I would have 1 is equal to 0 subtract U4. So that means U4 would have to be a negative 1. Because 1 is equal to 0 subtract a negative 1. So we have the solutions to the system. And I can write that the orthogonal complement of S is going to be the span of the set of vectors 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, negative 1. Now this is one of many bases, so you could write the base in several different ways, but that's one that would make it true. So that's one way of finding the complement, the orthogonal complement of S. Now let's let S1 and S2 be two subspaces of n space. If each vector x in n space can be uniquely written as the sum of a vector S1 from set 1 and vector S2 from set 2, in other words, x, which is a vector in n space, is equal to S1 plus S2, then Rn, n space, is the direct sum of S1 and S2. And we write that n space is equal to S1 plus, with a circle, S2. Now this should be read the direct sum. So I'd read this as the n space is the direct sum of S1 and S2. From the last example, 4 space is the direct sum of the span of S plus the span of the orthogonal complement of S. Well, to see this, let's go back and let's pick any vector from 4 space. So we'll let x be any vector from 4 space. So that means x is going to be of the form x1, x2, x3, x4. And we need to choose S1, vector S1, from set S1. Well, set S1 is going to be the span of S. So if we go back to the span of S, we see that we're going to have the vector. Here's the span of S. So here's S. S is the span of this set 0, 1, negative 1, 1. So a vector in that span is going to be in the form 0, C1, opposite of C1, C1. That's what we did before. So we'll say S1 is going to be of the form 0, C1, the opposite of C1, C1. Now, S2, vector S2 is going to be from set S2. When set S2, it's going to be the span of the orthogonal complement of S. So let's go back to S2. So for the example, this would be S2. Well, a vector here, vector S2, we can see is going to be of the form, if we use all different C's this time, this is going to be C2 plus 0 plus 0, so that would be C2, 0 plus C3 plus C4, zero plus C3 plus 0, 0 plus 0 minus C4. So S2 will be of that form. So I'll go ahead and put S2 here, which would be C2, C3 plus C4, C3, a negative C4. Now we'll see that we can write S1, vector S1, this is vector S1, vector S2. So vector S1 plus vector S2 is equal to X. Then we would have 0, C1, negative C1, C1, plus C2, C3 plus C4, C3 minus C4 is equal to the vector X1, X2, X3, X4. So S1 comes from set 1, S2 comes from set 2, X comes from 4 space. Well, this is going to give me C2, C1 plus C3 plus C4, a negative C1 plus C3, C1 minus C4 is equal to X1, X2, X3, X4. I can write this as the matrix equation with coefficients matrix, so to be 0, 1, 0, 0, 1, 0, 1, 1, negative 1, 0, 1, 0, 1, 0, 0, negative 1, times C1, C2, C3, C4 is equal to X1, X2, X3, X4. Now this equation has a unique solution. If and only if the coefficient matrix is not singular. Well, the coefficient matrix is not singular if the determinant is not 0. I'm going to leave it for you to use derive to do the determinant, but if you'll go to derive and do the determinant of this matrix, you will find that it is not 0, so therefore the equation has a unique solution. Therefore, any vector in n space can be written as the sum of a vector from S plus a vector from S complement. Let's look at a theorem. Let's let S be a subset of n space. The first thing that's true is the dimension of S plus the dimension of S complement, your orthogonal complement of S, is n. Well, we can look at the last example and see this, the span of S. Remember, S had only one vector in the basis. So we can see the dimension of S is 1. The dimension of the complement of S was 1, 2, 3. And of course, n was 4. So 1 plus 3 is 4. That's an illustration of it. 2 is saying almost the same as 1. That is that n space is the direct sum of a set and its orthogonal complement. So n space is the direct sum of any set with its orthogonal complement. And the third one is the complement of S complement is S. That should be intuitively clear to you, that if you start with an S, take its complement, and then to take complement of that, you're going to be back to S. Theorem. If U1, U2 out to UT is an orthonormal basis for the subspace S of R to the n space, and V is any vector in n space, then the orthogonal projection of V onto S is equal to V dot U1 times U1 plus V dot U2 times U2 plus out to and including V dot UT times UT. So we're defining the orthogonal projection of V onto S. Now V is any vector in n space, and S is the subspace of R to the n, and the U's form an orthonormal basis for S. Let's look at an example. Let's find the orthogonal projection of vector B is equal to 2, negative 2, 1 onto the column space of A, which is equal to 0, 1, 1, 2, 1, 3. Now, if we want to find the projection of B onto the column space, the first thing we've got to do is to make sure that we have an orthonormal basis for the subspace S of R to the N. Well, a basis for the column space of A is going to be the set of the vectors 0, 1, 1, 2, 1, 3. So, of course, we would have the basis. But we must make it orthonormal. Well, to make it orthonormal, the first step is to use the process in the last tape to find an orthogonal. So the first step is to get an orthogonal basis. Well, remember, to do that, we simply let W1 equal to V1, which will equal to 0, 1, 1. Now, W2 was equal to V2 minus V2 dot W1 over W1 dot W1 times W1. So W2 is going to be V2, which is 2, 1, 3, minus V2 dot W1. Well, here's W1, here's V2, so we'll do the dot. 0 times 2 is 0, plus 1 plus 3. So that's going to be 4 over. Okay, W1 dot W1 would be 0 plus 1 plus 1. So that would be 2 times W1, which is 0, 1, 1. So this is going to be 2, 1, 3 minus 4 divided by 2, of course, is 2. So it's going to be 0, 2, 2. So W2 is going to be 2, negative 1, 1. So we have the orthogonal basis, B prime, which is going to be W1, 0, 1, 1. W2, which is 2, negative 1, 1. Now, of course, step 2 is to get an orthonormal base. Well, what we do in both cases here is divide the vector by the length of the vector. So divide it by the unit vector. Or make it a unit vector by dividing by its length. So, we have the vector 0, 1, 1, and we're going to divide it by the length of that vector. Well, the length of the vector would be 0 squared plus 1 squared plus 1 squared. 1 squared is 1, 1 squared is 1, 1 plus 1 is 2, so it would be the square root of 2. So that's going to be the vector 0, 1 over the square root of 2, 1 over the square root of 2. 2, negative 1, 1. If we're going to divide it by its length, well, that would be the square root of a squared, b squared, c squared, so it would be 4, 5, 6 when I square them, because that would be 2 squared is 4, negative 1 squared is 1, 1 squared is 1. So 4 plus 5 plus 1 is 6. So this is going to be 2 over the square root of 6, negative 1 over the square root of 6, 1 over the square root of 6. So then we get that the orthonormal basis that I'm looking for is going to be 0, 1 over the square root of 2, 1 over the square root of 2, 2 over the square root of 6, negative 1 over the square root of 6, 1 over the square root of 6. Now, the orthogonal projection of vector B onto the column space of A is going to be B dot U1 times U1 plus V dot U2 times U2. Well, V, if we look, well, V is going to be taking the place of B. So the B was 2, negative 2, 1. U1 is the first vector in the set of bases, or in the basis set. So that's going to be 0, 1 over the square root of 2, 1 over the square root of 2. Times U1, which is 0, 1 over the square root of 2, 1 over the square root of 2. So this is the B. Actually, I probably should have written it as B times U1, dot U1 times U1 plus B dot U2 times U2. So it'll be plus now, B again, which is 2, negative 2, 1, dot, okay, U2, which is 2 over the square root of 6, negative 1 over the square root of 6, 1 over the square root of 6, and U2, 2 over the square root of 6, negative 1 over the square root of 6, 1 over the square root of 6. Okay, doing the dot product, that's going to be 2 minus 2 times the square root of 2 plus 1 times the square root of 2. So that's going to be a negative 1 over the square root of 2 times 0, 1 over the square root of 2, 1 over the square root of 2, plus now, that's going to be 4 times the square root of 6, plus 2 times divided by the square root of 6, that's going to be 6 divided by the square root of 6, plus that's going to be 7 divided by the square root of 6, times the u2 vector, which is 2 over the square root of 6, negative 1 over the square root of 6, 1 over square root of 6. So multiplying, this is going to be 0, a negative 1 times 1, that would be a negative 1 over 2, because the square root of 2 times square root of 2 is square root of 4, which is 2. And this is going to be a negative 1 over 2, plus 7 times 2 is 14. The square root of 6 times square root of 6 is 6, so it'll be 14 over 6, so that'd be 7 thirds. This is going to be a negative 7 sixths, and that's going to be a positive 7 sixths. Zero plus 7 thirds is 7 thirds. A negative 1/2 minus 7 sixths. Now negative 1/2 would be a negative 3 sixths. Negative 3 plus negative 7 is negative 10 sixths, which reduces to a negative 5 thirds. And negative 1/2 plus 7 sixths, that's going to be a negative 3 sixths plus 7 sixths, which is 4 sixths, which is 2 thirds. So the projection of vector B onto the column space of A is 7 thirds, negative 5 thirds, 2 thirds.